Hello students of Chem 330. Today's video will cover Navier-Stokes. The first part of this video will be using the equations to determine a velocity profile, and the second part will be applying that result. Part 1 is similar to the material covered in class and serves mainly for review. So to begin, we have a patient with abnormally high blood viscosity, and we're analyzing flow in a particular vein under known conditions, assuming that blood is an incompressible Newtonian fluid. We first want to determine which flow regime we're in by calculating the Reynolds number. This is the product of density, volumetric flow rate, and tube diameter divided by the product of dynamic viscosity and cross-sectional area. We are given the value for density. We can convert the given volumetric flow rate to SI units. And we are given the diameter of the vein of interest. We know that the blood viscosity is elevated to 10 times that of water, and we convert the result to SI units. Finally, our cross-sectional area is that of a circle, which can be calculated using the known radius of the vein. Substituting these values into the expression for the Reynolds number, our result is a value of 1548. And this number indicates that we are safely within the laminar flow regime. Before we begin working with equations, let's list our assumptions. We assume that the vein is long enough that end effects are negligible. This means that velocity does not vary with z. And so we can say that the derivative of vz with respect to z is equal to 0. We also assume that flow is at steady state. This means that all partial derivatives of v with respect to t are equal to 0. We'll assume that flow is in the z direction only, so Vr is equal to 0, and v theta is also equal to 0. Now we can apply these equations to the Navier-Stokes equation. Again, we are looking at velocity only in the z direction, so we have only one equation to simplify. From the steady state assumption, we know that the time derivative is equal to 0. We also assumed that Vr and v theta are both equal to 0. Because v theta is 0, there is no variation of the z velocity with respect to theta. And finally, from assuming negligible end effects, we know that the first and therefore subsequent derivatives of vz with respect to z must also be 0. Removing these terms leaves us with a very simplified expression. We can move del p del z to the other side of the equation. Just a reminder that this pressure is the modified pressure which accounts for gravity. Because Vz varies only with r, we can replace the partial derivative operators with total derivatives. Similarly, pressure depends only on the z direction, and the left-hand side of the equation can also be represented as a total derivative. Solving this equation will require two boundary conditions. The first we can get from the no-slip condition, which tells us that velocity at the wall is equal to 0. The second condition we get from radial symmetry, which results because v theta is 0. And this tells us that the r derivative of vz, evaluated at the center line where r equals 0, is equal to 0. So our solution will come from our simplified Navier-Stokes equation and our two boundary conditions. To begin, I'll move the viscosity term to the left-hand side, as well as the leading r variable. We can then integrate this expression with respect to r, resulting in this form with our first constant of integration represented by C1. We then need to perform a second integration, which results in an expression for Vz with our second constant of integration. Now that we have an expression for Vz, we need to determine the unknown constants C1 and C2. We can do this by applying our boundary conditions. Using the condition that the first derivative of Vz at the center line is 0, and applying this to the result of our first integration with r equal to 0, all terms except for our constant result in 0, which tells us that C1 is equal to 0. We can then simplify our expression for Vz and apply our second boundary condition. This results in C2 being equal to the opposite of the first term in our expression for Vz when evaluated at the full radius of our vein. We substitute this into the expression for Vz. We can then simplify this expression and substitute our known values from the problem statement, which results in this general expression for fluid velocity within the vein. We'll now move on to the second part of this video, where we'll apply the result that we just found. So for the patient described in the first part of our video, we want to remove blood through a pump at the end of half-meter long tubing, and we want to know the pressure that the pump will have to apply in order to remove half a liter in 1 hour. We have the expression for velocity in the vein, which we derived in the first part of the video. Since we're using tubing with the same diameter as the vein, this expression remains valid. We can represent the pressure derivative in the z direction as delta P over delta L. Because the flow profile that we determined is parabolic, we know that its maximum occurs when r is equal to 0. Evaluating our expression at r equal to 0, we get a simplified expression for Vz max. Vz average for the laminar flow profile is equal to Vz max over 2, which results in the expression shown. And finally, we know that the volumetric flow rate is equal to Vz average times the cross-sectional area. Evaluating the area with the known radius of the tubing, we get our final expression for Q. We convert the flow rate that we're trying to achieve to SI units, and substituting that value into the expression for Q, we can solve for delta P over delta L. We know that delta P over delta L is equal to our pump pressure minus that in the vein divided by the length of our tubing. We substitute our known values and set the result equal to the value that we determined for delta P over delta L. We can then finally solve for the pressure applied by the pump, which gives us a gauge pressure of 7,506 pascals for the pump.